Hello and welcome to Master Prodigy. In this video, I will be discussing our base 10 number system. Basically, a number system is a way to represent numbers. In math, we use a base 10 number system. We call it base 10 because it uses 10 different symbols for counting. These symbols we use are called digits, and they look as follows: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. We will look at different number systems like base 7 or base 13 in another video, but for now I will be considering the base 10 number system, which is the number system we all grew up with and are familiar with. The 10 digits 0 through 9 are convenient to count with, like when we count bananas, for example. When we want to represent no bananas, we write the digit 0, but as we start adding bananas, one at a time, we begin to count. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now, if we want to count higher than 9, we run into a problem, since we have already used all the available digits. In order to count higher than 9, we make use of a concept called place value. If we add one more banana, we will then have 10 bananas. We can then combine them to form one group of 10 bananas. This group of 10 can then be used in a new number place to count higher than 9. So when we count the amount of bananas from 0 all the way up to 9, we place the digit representing the number of bananas in what is called the ones number place. We call it the ones number place because the digit in that number place represents the amount of single bananas. When we add a 10th banana, we group them together to form a group of 10. We then create a new number place and call it the 10th number place. Since we have one group of 10, we then write a 1 in the 10th number place. Notice now that since we grouped all the individual bananas into a group of 10, there are no individual bananas left, and we therefore write a 0 in the ones number place. So that is how we represent the number 10. We can now count to higher amounts of bananas by following the same procedure. When we keep adding individual bananas, we continue counting. 11, 12, 13, 14, 15, 16, 17, 18, and 19. When we reach 19, we have once again reached the maximum amount of bananas we can add in the ones number place. By adding one more banana, we then form the second group of 10. Now that we have two groups of 10, we write the number 2 in the tens number place. This then represents the number 20. With our 10 digits and 2 number places, we can count all the way up to 99. Since both our number places are maxed out with the highest digits, we will need a third number place if we want to count higher than 99. So adding one more banana will create another group of 10, which will then amount to 10 groups of 10. The 10 groups can then be combined to form one group of 100. We then create a new number place and call it the hundredths number place, in which we write 1. Notice now that the ones number place and the tens number place both contains a 0. So with this new hundredths number place, we can further count in groups of 100. Are you starting to see the pattern? Do you see how our base 10 number system works? It uses different number places to represent the different size groups we use to count. And the digits in each of those number places tell us the amount of each group we have. The digit in the ones place represents the amount of ones we have. The digit in the tens place tell us how many groups of 10 we have, and the digit in the hundredths place tell us how many groups of 100 we have. Now of course it doesn't just stop at the hundreds place, it keeps on going. After the hundreds place, we get the thousands place. After that, we get the 10,000s place, then the 100,000s place, then the millions place. After the millions place, we get the 10 millions place, then the 100 millions place, then the billions place. It goes on forever, as high as we need for the number we want to write down. It is important to note that each time we added a new number place to represent a larger group of bananas, we added that new number place to the left of the previous number place. And every new number place represents groups that is exactly 10 times larger than the previous number place. 100 is 10 times bigger than 10, and a million is 10 times bigger than 100,000. So considering the number places in order from right to left, you constantly multiply by 10 with each bigger number place. Since the number place immediately to the left of a certain number place is always 10 times larger, the number place immediately to the right of a number place is always 10 times smaller. So when the number places are considered in order from left to right, you constantly divide by 10 with each smaller number place. So in a multi-digit number, the value of a digit is determined by the number place that digit is occupying. If the digit 7 is in the ones place, it just means 7. But if the 7 is in the hundreds place, it means 700. A 7 in the 10 millions place means 70 million. To further demonstrate this concept of place value, we can write a number in what is called expanded form. For example, we can expand 863 into 800, since the 8 is in the hundreds place, 60, since the 6 is in the tens place, and 3, since the 3 is in the ones place. So 863 in expanded form is a combination of these amounts. So up until now, we have only considered whole numbers, which we represented with whole bananas. But what if we did not have a whole banana, but only part of one? How can our base 10 number system be used to represent values that are not whole? The answer is with decimal places. Decimal places are just like regular number places, except they are used to count parts or fractions instead of groups like regular number places. The concept behind decimal places are exactly the same as with regular number places. Number places representing bigger groups are to the left, and number places representing smaller groups are to the right. But with the whole number places, we know that the place furthest to the right is always the ones place. But now that we have decimal places, which represents groups that is smaller than 1, they need to be added to the right of the ones place. In order to differentiate the decimal places from the whole number places, we use a symbol called the decimal point as a point of reference to show which places are the whole number places and which places are the decimal places. The decimal point is added just to the right of the ones place, and it looks just like a period. As mentioned before, when the number places are considered in order from left to right, you constantly divide by 10 with each smaller number place. When you divide a banana into 10 equal parts, you have 10 of what is called tenths of that banana. So where the ones place represents the amount of individual bananas you have, the number place to the right of it represents the amount of tenths of banana you have. And it is therefore called the tenths place. Now let us count in tenths of bananas. When we start with no whole bananas and no fractions of bananas, you write the digit 0 in both the ones place and the tenths place. This value is then pronounced 0.0, but as we start adding tenths one at a time, we begin to count. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9. Adding another tenth will form a whole banana, and we will then have 1.0. Continuing to add tenths results in 1.1, 1.2, 1.3, and 1.4. The number place to the right of a tenths place is called the hundredths place. A hundredth is what you get when you divide a tenth into 10 equal parts, and you need 100 hundredths to make a whole. So when we continue by adding hundredths, one at a time, we get 1.41, 1.42, 1.43, 1.44, 1.45, 1.46, 1.47, 1.48, and 1.49. Adding another hundredth will form a tenth, and we will then have 1.5. Just like with the whole number places continuing forever to the left, the decimal places continues forever to the right. After the hundredths place, we get the thousandths place, then the 10,000ths place, then the 100,000ths place, and then the millionths place, and so on. Writing decimal numbers in expanded form is exactly the same as writing whole numbers in expanded form. For example, the number 3591.874 in expanded form is 3000 plus 500 plus 90 plus 1 plus 0.8 plus 0.07 plus 0.004. Now when we are asked to find the place value of certain digits, it is easy to determine. We can easily see that the place value of 5 is the hundredths place, and the place value of 4 is the thousandths place. So you can see that with this concept of place value, we can use our 10 digits to count any number we desire, from 0 up to infinity. Now there are some additional notes to take. When we have a long multi-digit whole number like this one, it can be difficult to see which digit is in which number place, and as a result, it can be difficult to say the number. Therefore, many countries use some kind of separator every 3 places to make it easier to keep track of the number places. Sometimes a space is used, but the most common separator used is the comma. Without the separators, it is difficult to pronounce the number, but with the separators, it is easier to read 48,259,621,478. For decimal numbers, we never use separators between the decimal places. When pronouncing decimal numbers, we first say the value of the whole number part, and then we start saying the decimal digits in order from left to right. For this number, we would pronounce it as 9,572.84013, saying something like 9,572.84013 would be incorrect. We never pronounce the decimal digits like we do the whole numbers. For numbers with fewer decimal places like this one, we could say 10,496 and 57 hundredths. In this pronunciation, the decimal point is read as AND. I still, however, prefer the first pronunciation, where we set the decimal digits one by one in order from left to right. Using that pronunciation, this number would be pronounced 10,496.57. A final note to take is with regards to zeros. When we have a whole number like this one, we can discard off any zeros to the left of the last non-zero digit. This will not change the actual value of the number, since all those zeros just refers to zero groups of whatever size their number place represents. It is not incorrect to write zeros, it is just unnecessary. Take care to not discard of any zeros to the right of a number. Doing so will change its value, since those zeros are still required to indicate place value within the number. Zeros to the right of the last non-zero decimal digit can also be discarded for the same reason. It also does not change the value. When we have only zeros after the decimal point, like with this number, we can discard the zeros along with the decimal point, since this is actually just a whole number and contains no fractions. Once again, it is not wrong to write a whole number with a decimal point and zeros after it, it is just unnecessary. So that is everything about our base 10 number system. Now that we know how our number system works, we can start learning about arithmetic, and that will be the topic of the next video. Thanks for watching, and remember, always stay curious.